And welcome everyone to, of course, a lot of students in this class, ESC 6242. And also today, our guest lecture, we also branded it as a machine learning seminar talk. So we also have people on the campus coming who are not a student in this class, but welcome, all of you. And today, we're really happy to have our colleagues from MailChimp, who's a local company. They are based in Pond City Market. They have now 3 floors there. If you've ever been to Pond City Market, you've probably already seen their logo. Really happy to have them today to come give us guest lecture and delivered by Mohammed Ahmed, who is a data scientist at MailChimp, and who will be talking to us about the natural language processing approaches, or NLP approaches, that they're using on campaign classification. So MailChimp is the world's largest marketing automation platform. And Mohammed there is a data scientist role at MailChimp, and he graduated from the University of Georgia, or UGA, and we'll forget about that, and with a degree in computer science and a certificate in applied data science. So good news is that Mohammed recognized that that was not quite right, so he will be starting as an OMSCS student in June, so coming to the bright side, yes. So Mohammed specializes in NLP, natural language processing, and has implemented several deep transformer models and for text classification tasks. And his models are used for spam detection, business vertical classification, and also support ticket classification. So without further ado, so let's welcome Mohammed. Yes. Go.
Thanks, Polo, for that awesome introduction. Yeah, like Polo said, I'm Mohammed Ahmed. I'm a junior data scientist at MailChimp. And today I'll be talking to you about NLP approaches to campaign classification. So first we'll start with an introduction, and then we'll move on to a broad overview of word embeddings. And then we'll look at a specific example that I use at MailChimp for campaign classification, and then we can take a look at future directions. So first, I kind of want to introduce MailChimp and like what even is a campaign. So MailChimp is the world's largest marketing automations platform. We send about 1 billion emails a day, and we're primarily known for this email sending capability. That email that you send is an email campaign, and so the work done here is on classifying the text content in that email. So I'll start with what this talk is about. And so the goal here is to provide a broad overview of text classification methods in NLP, focusing on the ones that are most empirically successful as of today. And also to provide a summary of the recent advances in text classification such that by the end of the presentation, everyone has an understanding of state-of-the-art NLP approaches. And then lastly, I want to offer my recommendations for building a high-performance campaign classification system. But generally, this will apply to text classification as a whole. So if you're doing any of this in your own research, this might be helpful to you. And what it's not is comprehensive, as it'd be impossible to cover all related papers in one talk. And also, I want to practice the Bender rule, which is to explicitly state the language in which we're working in, which is English. We want to avoid treating English as the default unmarked and normative language, as it plays into all sorts of unfair narratives about who counts as intelligent. So to avoid that, all this work is in English. So now I can provide the motivation for why we might want to classify email campaigns. And so the first is listening hard. This is one of MailChimp's company mottos. Like I said, we send about 1 billion emails a day. So we should at least make an attempt for understanding what our users are sending. The second is customer business vertical prediction. So this is given an email campaign predicting what kind of business the user has. And this can be used to in features like the campaign performance comparison, otherwise known as benchmarking, or to surface smarter recommendations. It's also used in in-house spam detection. So spam detection is probably something you're used to hearing about on like the receiving side of an email, but it's really helpful on the sending side as well because we can preserve our IP reputation and prevent users with malicious intent from using our platform. So I kind of wanted to give like a broad overview first of what campaign classification might look like. So you can see, that, and this is a specific example of customer business vertical prediction. So you have like a campaign, and you feed it into an embedding technique, in this example, BERT, which is a technique that we'll talk about in a bit, and then feed it to a classifier, and then finally that classifier will output some prediction. So now we'll start with like a broad overview of embedding techniques and then end with how we resulted on BERT. Word embeddings are just these numerical representations of text. That could be like a word, a sentence, or maybe just a sequence like an entire document. And machine learning models, they can't take in like raw text by themselves, so you have to convert it into these embeddings. And throughout this presentation, I'll probably switch between saying word embeddings, vector representations, word vectors. These all mean the same thing, so don't let my terminology confuse you. So bag of words is the kind of off-the-shelf and simple way to create these representations. You basically just create a histogram of counts of word occurrences, and then you can apply different weighting schemes, TF, IDF, for example, to account for term frequency across documents. The problem here are that these mappings are a bit arbitrary and provide no useful information about the relationship between words. So we can look at this example where we have this vocabulary and an input sentence, I like dogs. And we can see the vector representations of each of these words. And the issue here is that if I was to compute the similarity between dogs and cats, it'd be the same as the similarity between dogs and I, which isn't very helpful to a classifier. So it turns out, rather than being arbitrary, these representations can be learned through a process called language modeling. And the whole idea behind language modeling is to utilize the distributional hypothesis. And that is that you shall know a word by the company that it keeps. So language modeling informally is estimating the probability of text given some other text. You can think about this as the fill-in-the-blank example. We have a blank and 3 dogs, and I give you the task to fill in that blank. You can formalize this into a mass language modeling task of filling in the blank or predicting the next word, which is an autoregressive task. And the advantages of language modeling are that we're able to utilize the unlabeled data through this self-supervision process. And many languages contain enough language or text to learn a high-capacity language model because it's really easy to gather large corpora from, say, Wikipedia, a web crawl, or social media. And it's also very versatile in that you can learn both sentence and word representations, and in our example, campaign representations, using a variety of loss functions. Language modeling works really well because it's inherently a difficult task, even for humans. And for the model to have any chance at solving this problem, it's forced to learn semantics, syntactics, and how to encode facts about the world. And empirically, it works better than translation, which was the previous approach to creating these representations. And so given enough data and compute, a high-capacity model can do a reasonable job at this. So a word-to-vect is a shallow neural network approach that generates these high-quality non-contextual word vectors that are able to capture semantic similarity. So it performs this center word prediction, that language modeling task. And you see, if you were to plot the word vectors in Euclidean space, you can see it's able to capture the semantic similarity. For instance, man is to woman as king is to queen, but also syntactic relationships. So going from the gerund form of these verbs to the past tense form. The problem with these word vectors is that there only exists one word vector per word. This is problematic because we know that in English, you can have multiple meanings per word dependent on the context in which that word exists. For example, we know that the word vector for play, given the source sentence, the kids play a game in the park, should not be equal to the word vector for play given the Broadway play premiered yesterday. Similarly, what do we do for pronouns like it that refer to other words in the sentence? The sentence here is the animal didn't cross the street because it was too tired. We realize that it refers to animal, not street, because streets can't be tired, but there's no way for a low-capacity model like this to understand that sort of relationship. So that's where contextual embeddings come into place. So contextual embeddings take in the entire sequence in which a word exists before assigning a word vector. And Elmo was one of the first approaches at creating these contextual word vectors. By the way, shamelessly stole this from Jay Alamar's blog post. It's a really great one on the illustrated transformer. This is kind of just like a playful skit. So it goes, you ask Elmo what the word embedding for the word stick is. Elmo says, use it in a sentence. You provide the sentence, let's stick to improvisation in this skit. And then Elmo outputs a contextual word vector. It does this by training a bi-LSTM first in the forward direction to predict what the next word is, and then in the backward direction to predict the next word, but in reverse. We put in the sentence, let's stick to, and so the task would be to learn improvisation. But also in the backward direction, you can learn to stick let's, and then the task would be to learn, say, the start token of the sentence. So you have these two LSTMs, and you concatenate them layer-wise and then you compute a weighted sum, and then the result of that weighted sum is your contextual word vector for the word stick. And this achieved state-of-the-art on 6 diverse data sets back in June of 2018. In a lot of this presentation, I'll have results tables. I've highlighted the ones that are most relevant to us. SST is a classification data set. It's kind of like a natural language understanding benchmark. And the number at the end always stands for the number of classes in the problem. So this is a 5-class classification problem. And so you can see the output of Elmo is these contextual word vectors that are dependent on which the context that the word exists. So now we'll move on to transfer learning, which is a slightly orthogonal point. So transfer learning is storing knowledge gained from one problem and using it in a related but different problem, such that the learned rates from the previous problem are used as the starting point in the brand new problem. You can think about this in the movie review classifier example if we want to take in movie reviews and output positive or negative sentiment. One thing you might do is train a language model on a very large corpus to learn that mass language, or maybe predicting the next word on, like, say, Wikipedia. And then you can fine-tune that language model on your downstream data set. So this would be IMDb movie reviews. The intuition for this is that when you language model on Wikipedia, you're learning general semantics and syntactics about English as a whole. But when you fine-tune to your downstream data set, you're learning more domain-specific things. So in our example, maybe different actors' names and how they relate to other things. Finally, you perform network adaptation, which is where you chop off the head of the classifier. You freeze the rest of the weights of the network, and you only train that classifier head. And so the motivation for transfer learning and natural language processing is that NLP tasks share common knowledge, like, for example, linguistic representations and structural similarities. And it also provides really good sample efficiency and performance. So ULM Fit, which is the paper that we'll talk about next, performed an experiment where they used 3 different levels of transfer learning. And this is a validation error plot, by the way, so ideally we want it to be as low as possible. So the blue line is using no transfer learning, and the orange line is using 1-stage transfer learning, and the green line is using that 2-stage transfer learning where we language model on Wikipedia, and then our downstream data set, and then finally the classifier. And you can see in fewer examples, it's able to achieve better accuracy. So that achieved state-of-the-art on 6 classification data sets back in May of 2018. They used 2 really clever techniques in the paper called discriminative fine-tuning and layer unfreezing. So discriminative fine-tuning is just applying different learning rates at different layers of the network, where this is the output layer. Specifically, you want exponentially decaying learning rates, so the latest layers learn the most. And then layer unfreezing would be to freeze the rest of the network so you don't train any of those weights, and you only train the top layer, and then you slowly unfreeze and you train a little bit more, and then you unfreeze all the way until you're training the entire network. The intuition for both of these approaches is we want to avoid this problem called catastrophic forgetting during transfer learning, because we don't want to forget all the valuable information that we learned from, say, the Wikipedia language model in going to this new task. So it's kind of like easing the classifier into this new task. And so this whole talk could probably be about transfer learning, but instead I'll just give you a few major themes and takeaways from the papers. And that's generally that more data results in better reward vectors, bigger models result in better results, and pre-training for a longer time also generally results in better results. And now we'll talk about attention mechanisms. But before we talk about attention mechanisms, we should address the weaknesses of recurrent networks, which was the previous architecture that we're using to create these representations. So we can return to our sentence, the animal didn't cross the street because it was too tired. We need it to attend to the representation for animal. And in this recurrent structure, you take in one word at a time, and the output, the hidden state of the current word feeds into the input of the next word. So what we would need to do to get the hidden representation for animal is get the output or the hidden state and have it travel all the way to it losslessly. But what actually happens in practice is by the time that the representation gets to it, it's a bit noisy if it even exists at all. And then there's the parallelization concerns, and that goes with this being an autoregressive task where the input to the current node is the output from the previous node. You can't really take advantage of these high-performance GPUs. This is more talking about the long-term dependency issue more. So the blue score is used in language translation. It's basically to tell you how good your language translation is working. And you can see that generally as sentence length increases, the blue score decreases. So what is attention? We can start by the way that it's motivated, and it's motivated by the way that we pay visual attention. So if I give you the task of identifying what's in the yellow box, you might use some of the things in the red boxes to inform that decision. What you might not use are the things in the gray boxes because these are less like doggy features. So it's just kind of this idea that there's some things that you can ignore and some things you can attend to. And we can take this back to words and look at our example sentence, the animal didn't cross the street because it was too tired, and visualize the attention weights and see that it can attend to animal. And if we were to change one word to now the animal didn't cross the street because it was too wide, we see that the attention weights update such that it attends to street now. And the transformer architecture was the first to kind of have this idea to fully get rid of recurrent networks, CNNs as well, and just use attention. The only really important part that you need to know about the transformer architecture is that there's a stack of encoders and a stack of decoders, and within each are two different types of attention. So the encoder has self-attention that's able to see the entire sequence that you input. Masked self-attention is in the decoder. It's only able to see up to the word that you're about to predict. The intuition for this is that during training time, you don't want to feed the word that you're trying to predict whilst trying to predict that word, because it'd be cheating. So OpenAI's GPT pulled out components of the transformer. It took that decoder with the masked self-attention, stacked 12 of them on top of each other, and got state-of-the-art on 9 tasks back in June of 2018. And so you can see it's performing this next word prediction task. So you input your sequence, and then you pass it through the transformer's architecture, and then finally to a classifier, and then you output some result. The problem with this is that sometimes future context is important. So we can look at these two sentences and see that Mark can be used as a verb or a noun, and it's only decided in later words in the sentence. So if I'm coming up with the representation for Mark, I'll first read these sentences. So it's Mark, which area you want to distress, and then Mark, which area do you want to distress? So it's just the idea that future context is really important, and having these masked out tokens can be really harmful to creating these representations. So that's finally where BERT comes into place. So BERT takes all of these ideas of all of these things that I just described and puts them all together. So contextual embeddings from Elmo, transfer learning from the ULM Fit paper, the attention mechanism from the transformer paper, and similar to OpenAI's GPT, it pulls out components of the transformer. Specifically, instead of pulling out the decoder, it pulls out the encoder that's able to see the entire sequence. BERT comes in 2 sizes, BERT base and BERT large. And within those, there's a stack, in BERT base, there's a stack of 12 these transformer encoders, and in BERT large, there's 24. BERT has 2 pre-training tasks. So the first is masked language modeling. That's where we input a sentence and mask out 15% of the tokens, and then predict what that masked token is. And then there's next sentence prediction. That's where we have 2 sentences, and we predict whether sentence B comes after sentence A. So I can read these 2 examples. So sentence A is the man blank to the store, and sentence B is penguin blank are flightless birds. Those sentences don't really sound related, so the output is not next. And this pre-training task was done on a very large corpus of books, as well as English Wikipedia. BERT base was trained on 4 cloud TPUs in a pod configuration, and BERT large was trained on 16. And each pre-training task took 4 days to complete. And so luckily, you don't have to pre-train BERT yourself. These are all available to you to use. So these are the different variations of BERT. So like we said, there's base and large. But within those, there's case and in-case sensitive. So if your problem relies on uppercase and lowercase being a distinction, then maybe you want to use cased. But there's also the multilingual case and uncased BERT, as well as Chinese simplified and traditional. And this is just to speak to the successes of BERT. So as of June of 2019, BERT was state-of-the-art over all existing systems on all, I should say, natural language understanding tasks by a large margin. These include text classification, language translation, question answering, summarization, and natural language inference. So now we can move on to a MailChimp-specific example of campaign classification. I'm going to take a drink of water. So we'll return back to our example of predicting a customer's business vertical given their email campaign. And so we'll be using BERT. So in this example, once again, you feed in a campaign, you pass it to BERT and get this numerical representation of the campaign, and then pass it to a classifier. The classifier part actually doesn't really matter. BERT's doing all the heavy lifting. So the classifier here is actually just a single layer. And then you output some prediction. And then I'll talk about the data a little bit. So at MailChimp, we have about 10 million unlabeled users in terms of their business vertical. Our labeled users come from kind of this historical, when you were onboarding and creating your MailChimp account, it used to be a part of onboarding to select your industry. This is no longer a part of the app, so there's kind of been this initiative on the data science team to label some of these unlabeled users. This is a 46 class problem. You can see some of the examples here. There's like architecture and construction, there's like beauty and personal care, construction, etc. Among these, there's a very high class imbalance. And then this was all trained on only the publicly available campaigns to respect our users' privacy. And then there were data pre-processing steps. So that was to strip out some of the campaign structure. So this included like signature lines, all rights reserved text, like copyright symbols and stuff like that kind of appear in every single campaign and isn't really representative. And then I removed the non-English campaigns via a language prediction software. And then use word piece tokenization. So tokenization is where you have your entire campaign as a string, but you want to get it into a list of words, and tokenization is the way that you go about that, using a predefined vocabulary. A common problem in NLP is determining what this predefined vocabulary is. Because when you output your model to the real world and you start using it, you don't know what words you're going to come across. But one thing you can do is use a clever technique like word piece tokenization, that when a word isn't available in that vocabulary, it's able to split words along these morphological boundaries. So you can create representations for words using like root words. And then there's label smoothing. So there was a fair amount of class entanglement. So label smoothing is a regularization technique you can use to basically make sure your model isn't like too certain of one class. And then there's a train test and validation split. There were a few network adaptations. So this was to fine-tune the language model using sequential unfreezing and discriminative fine-tuning, like we saw in the ULM fit paper. And then I applied class weighting at the loss function during classification to account for this class imbalance. So this is two-stage transfer learning. So the first stage, we want to fine-tune the language model. So we're predicting, say, well, in BERT, we predict the masked word. And we're using email campaigns, which are our downstream data set. So that took 60 hours on 2 NVIDIA T4 GPUs with the following hyperparameters. And so the second fine-tuning step is fine-tuning the classifier. And this took 10 hours on the same 2 NVIDIA T4 GPUs. And this is a table of results. You'll notice it's split down the middle. That's because we can kind of think of the output of this model in 2 different ways. So the output is going to be a list of size 46, where each index in the list corresponds to the classifier certainty of that campaign being of that class. So you can think about this 2 ways. Either you can take a single prediction, which would be the one with the highest confidence, or you can set a confidence threshold, say 0.7 in this example, and take only that subset of very confident values. So now we can look at this, and top to bottom, it's just kind of advancements that happen over time. So we can observe the F1 score when I used the vanilla BERT and didn't fine-tune it. It didn't perform so well. And then I fine-tuned it, and it got better. And then I applied class weighting, and it got much better. Added more data, because that always helps. And then I improved the language prediction. So I explained that was like a pre-processing step to strip out any non-English campaigns. A really interesting thing that I found is that a lot of these language prediction softwares, if you feed it like punctuation along with text, like German text and punctuation and like numbers, it's going to think it's English for some reason. There must be some bias going on in the model. But I found that out afterwards, and since then stripped out all of that, like the non-letters, and improved the language prediction, which then improved the downstream classifier. And then finally, I added even more data, and that resulted in the best results. And you can see for the same case for the multi-label prediction as well. So when I was making this presentation, I thought I would do a demo of, it'd be really cool to show you guys like campaigns and like what the classifier said. And I started with correct predictions. It turns out that's not very interesting. So we're going to look at incorrect predictions instead. So there was a common problem with image campaigns being especially troubling for the classifier, because obviously if the entire campaign is like an image, there's no relevant text for the classifier to take in. So this entire thing is pretty much just an image. So the classifier got really confused. Oh, by the way, the self-reported business vertical, which is the ground truth label, was restaurant and venue here. But it got really confused and said things like e-commerce, online communities, hobbies, and retail. Here's another example of a just image campaign. I think this entire green thing is just one image, and their self-selected business vertical was e-commerce. You can see here that e-commerce actually, it still got pretty confused, but e-commerce actually did end up somehow here. I think this is because the Shop Now button is actually text. Here was a much rarer case. So this was non-representative text. So this was where none of the text in the campaign actually contributed, or it didn't look like anything that's representative of the business vertical. So their self-reported business vertical was games. This is an organization called the IGDA, the International Game Developers Association. They never said anything about games in the document, and they always use their abbreviation. So the classifier said that they were nonprofit with a really high confidence. I was really curious why the confidence was so large. And then I looked up the IGDA, and it actually is a nonprofit company. So not bad. My takeaway was that maybe their language was just that of a nonprofit company. So it got it right, but like wrong at the same time. And then there were examples of where users would self-select their business vertical incorrectly, so the label was false. So this is from an organization that identifies themselves as the best food importers. But they self-selected their business vertical to be architecture and construction, which is not true. So the classifier actually outputted agriculture and food services with a really high confidence. And then there were examples where the classifier is wrong, but like still reasonable. So Memory Cross is a company that sells like Christian mugs and stickers with proverbs on them for kids. So they self-selected their business vertical to be manufacturing. But the multi-label predictor outputted religion and e-commerce, which I would actually say is probably more representative of what they do. Here's another example. So this is Grace Point Church. They are self-selected their business vertical to be nonprofit, which is true because most churches are nonprofit. But the multi-label predictor outputted religion, which is also true because churches are religious. I think this is the last example. This is Old Garden. It's a DIY plant campaign. They basically teach you how to tend to your plants, and so they self-selected their business vertical to be education and training. The multi-level predictor outputted home and garden, agriculture and food services, and hobbies. So the best way to probably get your feet wet with BERT would probably be to try it out yourself. So if anyone was interested, these were the 4 implementations that I would recommend, especially the PyTorch implementation. It's especially good, and the NLP community is really bullish on PyTorch. I think in 2019, about 80% of all the new NLP papers use PyTorch. So if this is something of interest to you, then maybe you want to learn PyTorch. So now I'll provide the overview of guidelines of building a high-performance campaign classification system. Most of these techniques will apply to the more broad text classification task. And that would be to fine-tune your language model as it produces better results in a fewer number of epochs, and to use discriminative fine-tuning and layer unfreezing like we saw in ULMFit. And then using your embedder, you want to extract the final hidden state. And then use class weighting if you have any class imbalance problem. And then strip out the campaign structure. So this would be like the sectional dividers and the all rights reserved text, and anything else that's not really representative or anything that's really generic across all of your examples. And then for BERT specifically, you want to keep things like punctuation. URLs also turned out to be very predictive. Specifically, if you want to fine-tune the language model, you're going to need periods because there's that next sentence prediction task. So it's the only way it's going to know that there's sentences. And then remove any non-letters if you plan on limiting to one letter or doing any language, or one language and doing any language prediction. And then, if at all possible, obtain more data. We saw that in my example, every time I added more data, it seemed to boost performance. So now we can look at some future directions. So the first three are just variations of BERT. So BERT came out like earlier this year, like it's been out probably about like 9 months. So a lot of different variations of it have come out since. And then the other two are just different classes of deep learning architectures that we might want to apply to campaign classification. So the first is RoBERTa. It stands for the Robustly Optimized BERT Approaches. It came out of Facebook AI, and they basically just trained it longer on bigger batches with more data, and they removed that next sentence prediction objective, as it turned out to be not that helpful. And then they trained on longer sequences as well, and achieved state-of-the-art back in last month, actually. And then this is kind of just looking over time, the size of deep learning models getting larger and larger. And then so that points to the question, when do these models get back down to like a reasonable size to train and use in practice? And DistillBERT answers that question. So DistillBERT uses student-teacher training, which trains a student network to mimic the full output distribution of a teacher network, where the teacher is BERT and the student is DistillBERT. It's able to retain 95% of BERT's performance on these natural language understanding glue tasks, and only using half of the total number of parameters of BERT. It does this by minimizing the KL divergence between the two output distributions. And then we have Albert. This is the current state of the art in all natural language understanding tasks. It came out 2 weeks ago. And this is it's pretty much the same architecture as BERT for the most part, where we have the transformers encoder and a stack of them, and GELU nonlinearities between. And then they use the additional data and larger batch sizes from RoBERTa. Its three main contributions were that it provided parameter efficiency through parameter sharing and embedding factorization. And then instead of, so RoBERTa removes that next sentence prediction task. They instead replace it with sentence ordering, as that turned out to be a lot more helpful. And then they remove the dropout probability altogether. They performed an ablation study in the paper where they showed that all levels of dropout seem to perform lower than just getting rid of it. So now we can look at different classes of machine learning architectures that we could use. So this is multimodal campaign classification. So we saw that images were like a common problem, like just campaigns that were just images. So what if we embed the image as well? And where this is, say, like BERT, and we use like a ResNet or maybe like VGG or something to embed this image, and then we concatenate them, and then use multimodal self-attention, and then output a result. So this is something that I'm really excited to try out. And then I think this is my last slide. So this is multitask learning. This is something that's really popular in the research right now. So all the models that we looked at today actually have only one task. It's either like language modeling, where you want to predict, like, say, the next word, or classification, where you just want to predict whatever the class was. But what if we did like the two at the same time? And it turns out to be a really empirically successful method, so long as the two tasks are related and able to inform each other. So the way you could like define the loss function would be the sum of your primary task times some auxiliary task and multiplied by this annealing ratio. And that's all I actually have today. So thanks for listening to this talk, and we'll take questions now.
Okay, thank you very much. So we have plenty of time for question, and also we have a lot of swag here on the table, which you can have some at the end, not now. So then, yes. So we have a lot of time for Q&A, and any questions that you have of Mohammed, and also want to say that so MailChimp is hiring a lot of people. I think they're going to plan to grow by what, 50%, 50. So a lot of people, and they already have 3 floors in Ponce Market, so I don't know how many hundreds they're hiring. And also they have interns positions, and also full-time positions as well. Okay, so questions from the audience. Yes. Okay, don't be shy. Oh, maybe I'll start with one question first. So the looking at those numbers, so you said a lot of these are state-of-the-art and seems to look great. So one often the question that, I think especially this class where we say doing data and visual analytics, right? And then there's this part about visual, like visualization. So what's your impression looking at these models? That they're already doing great? We don't really need any human anymore. We can just do everything automatic. And then, so what's your experience, your thoughts on that?
Yeah, no, really good question. So my impression would be there's like an entire spectrum when it comes to classifying things when you work on like a product team. One side of the spectrum is to just fully predict for your user. And then the other side would just be to put all of the labeling tasks onto your user. But what you can do is kind of come together. So similar to how when Facebook, they show, they'll put a bounding box around your face and say, is this you? They don't label it. They don't say this is you, and they don't ask you to find all the pictures and draw the bounding boxes. I think the best approach probably would be to have that kind of like symbiotic relationship where you provide a bunch of maybe like your top 5 predictions, and then your user will self-select.
I see. Good. Yes. Question? Yeah, over there. Yes. Go ahead.
I'll go and speak, I think, if I can hear you. So the question is if I use these big models in production. Most of them that you've seen here today I've used in practice, especially BERT and Roberta, which came out of Facebook AI. We're currently productionalizing some of this business vertical model prediction stuff. We're currently using this. So the question is, when in production, how do you debug these models? So luckily, we work on product where it's user-facing. So there's a few UI components that we can create for that. That's where we, like whenever we predict a customer's business vertical, we explicitly state that we predicted. And there's a section where you can fill in feedback to ask if we nailed this prediction, could we have done better? And then like a little text box where you can add any additional comment. By debug, exactly what do you mean?
So let's say there's a data point where the model did not perform right. So how do you fix that?
There's not much you can do on like the individual level when you do work on, and specific to the model, but luckily not all problems have to be solved by like machine learning. When you work on like a product team, you take what's usually known as like the MVP or like the minimum viable thing. So in that case, it would probably just be to have users be able to self-select if your prediction was wrong. And luckily, we're working on, like, it's not like a tumor classification, so we're just working on predicting customer verticals, so there's not much risk there. But thank you.
Yes. Oh, yes.
Hey.
More about one of the papers you talked about. One of the more recent ones you talked about how removing dropout made it better.
That's right.
Is there any other kind of regularization, or is it just like, regularization is dead, we're just overfitting like crazy?
Yeah, it was really interesting. Like they only had like a few sentences about it. I thought that same thing. It turns out, at least the justification that they gave, was that in previous works, using CNNs and RNNs with like batch normalization and dropout seemed to prove empirically and theoretically to be like lower performing. And that's kind of like the only backup that they gave for that answer.
So they did use batch norm in this?
Yeah. So, well, BERT itself uses layer norm, which is kind of like, it's very similar to batch norm. So, yeah.
Other questions? Okay, maybe I will have a question, high-level question, not specific to NLP. And so you work as a data scientist role at MailChimp, and I know a lot of students in class are interested in a position similar to that. And so I understand that you got recruited, or you started working at MailChimp, like originally started with an intern, is that
Yes.
right? Yes. And then you joined the company. So what experience can you share with students who might not have worked at a company yet, and what are some like good skills, essential thing that you think are helpful to prepare and so on. Yeah.
Yeah, so I was a summer intern as well as a fall intern while I was still in school. It's really awesome at MailChimp in that you're able to have all the responsibility of like a full-time employee. Like you're giving real tasks, like real tickets, where your team depends on you, and you're immediately given the trust in like your competency and that you'll do good work. So that was like really awesome. And then for preparedness, I would say that just coming humbly and with eagerness to learn is probably the best piece of advice that I would give.
That's great. So how about like technical skills wise? So do you need to know certain things already, or is that I'm sure there's an expectation that you continue to learn over time at work and so on. So are there certain things that you think, okay, so really need to have these before you even attempt like applying for any? Yeah.
There's such a broad depth of problems that you might work on. So I can't say there's one thing that you should directly like specialize. I would say just making sure that your foundation is probably as sound as possible. And during your interview, as long as you don't try to pretend like you know something. If you don't know something, I did this during my interview. If you don't know something, just say it. It's much more comfortable for you and the interviewer rather than like listening to you like lie about knowing something.
Yes. Yeah, actually that's a good, I would want to make that good comment is, so sometimes interviewers, depending on who you're talking to, sometimes they may try to trap you a little bit. They may ask you, do you know about this? And if you pretend that you don't, pretend that you do, but you actually don't, then okay, no hire, sorry, reject. So don't pretend. Any other question from the audience? A very, very shy class. Okay, and I don't know, are you guys like accepting resume or things like that?
We have currently some position open, so
okay.
it's still open. It's not going to be open for long, so
okay.
And then we have another wave of opening coming in a few months.
I see. So they will have something coming up, that position coming up. Okay, great. Okay, so without further questions, let's thank our speaker again. Thanks.